question here.
So what would have to happen for it to concentrate in the transgolgi network?
What would have to happen to, you'd have to block secretion and cells would die. So there are some drugs that you can do that with, but no, you don't need a signal at all. Question here, or comment? Question or comment?
Some of you may be thinking that if there's no glycosylation, there's no proper folding in the ER, and then things will accumulate in the ER. But if, as Dr. Halloran just mentioned earlier today, if proteins are not folded properly in the ER, say because they miss a glycosylation, then they will be transported back to the cytoplasm to be destroyed by the proteasome, so they will not accumulate in the ER. So either way you cut it, these cannot happen.
Yeah. Okay. Other questions? Okay, so let's talk then. What we haven't talked about is how the mannose-6-phosphate receptor releases. It's the same story you've heard before. The mannose-6-phosphate binds lysosomal enzymes in the transgolgi network, and then will release them in the late endosome, which becomes a lysosomal enzyme. So how do we get it to bind here in the transgolgi network, but release them and then travel back in empty form back to the transgolgi? And as I pose that question, it may sound sort of familiar because the same question we posed with the KDEL receptor, and the principle's the same. So the mannose-6-phosphate receptor is the binding of its ligand, mannose-6-phosphate, is really sensitive to pH. So it will bind in the slightly more neutral pH of the transgolgi network, but then will release in the more acidic pH of the late endosome pre-lysosomal compartment. And it will release the lysosomal enzymes, then go on to this as this compartment matures into a mature lysosome, and the receptor will travel back in vesicles back to the transgolgi network. And this is a new kind of vesicle that we're not going to cover the codes for, but it's been discovered in the last 5 years. And I didn't feel like adding another kind of code to y'all, so we're not going to talk about that code. And then there it can bind again. So the principle is the same as the KDEL receptor. It's because the mannose-6-phosphate receptor is exquisitely sensitive to pH. Okay, so let's end now talking about, in the last 7 minutes, endocytosis, how cells get from the how proteins get from the plasma membrane back to inside. And the pathway that we're talking about is going from the plasma membrane, vesicles bud off from the plasma membrane and fuse together to make an early endosome. That will then become a late endosome. So the late endosome is actually getting lysosomal enzymes that will become here, as well as traffic from the early endosome. And that's what I was saying. These compartments are fluid and they aren't defined really. And so we're going to look at this step, how proteins get from the plasma membrane to the inside. And that's using a coat that we've talked about before. That's the clathrin plus AP2 coat. So we've talked, so we're looking at here how endocytosis goes from the plasma membrane to early endosome. This talks about the continuous flow. This shows clathrin coats right here. So, and this shows the difference between AP1 and AP2. So those are remember that the clathrin has 2 kinds of coats. These proteins, when purified and you look at their structure, look somewhat like Mickey Mouse right here. The AP2 code, the AP1 code is at the clathrin plus AP1 is at the transgolgi network. Clathrin plus AP2 is at the plasma membrane. So that's the code we're going to talk about now as we talk about endocytosis, is clathrin plus AP2. And I want to talk about that with talking about how receptors are internalized into clathrin plus AP2. And it's the same story that you've heard before. This internalization of the receptor is based on a signal. In this case, the signal can be one of 2. One is a tyrosine-based signal, so proteins that have tyrosine, along with some surrounding specialized amino acids. will go from the plasma membrane to endosomes. And there's another signal that's used sometimes, a dileucine signal, so two leucines together, will also be on receptors that are going to go from the plasma membrane to the endosome. And the way those work was first worked out by the Brown and Goldstein lab in Dallas, UT Southwestern. So I've referred to their work before as we talked about how they won a Nobel Prize for many aspects of figuring out how cholesterol works in the involvement of cholesterol in cells, how cells regulate their internal cholesterol, and also why high levels of cholesterol can result in cardiovascular disease. They were seminal in working out the cholesterol lowering, the science behind the cholesterol lowering drugs that are so popular today and have actually decreased the number of heart attacks we have around the world, the statins. So this is so cool. So they worked out that the LDL receptor is high in liver, and it is internalized in, this says coated pit. You all realize that's a clathrin plus AP2 coated pit. And what they found was that receptors that bind to LDL will internalize the LDL into cells through clathrin plus AP2 coats. The coat falls off. Those fuse together to make early endosomes. And then in a sorting process, LDL is delivered to lysosomes where it's digested, you make cholesterol from it. This cholesterol can be used by cells in their plasma membrane and other organelles. And then the receptor travels back up empty, ready to pick up more LDL. So without this pathway right here, you wouldn't have a way to bring in LDL into the cells. And the way that they identified the signal on the LDL receptor is fascinating. So they used, instead of sequencing LDL receptors the ways that we talked about finding receptors before, instead they looked at patients that had high LDL in their blood. So high LDL in your blood, that's the bad cholesterol, and it's the bad cholesterol because if you have high LDL, you're much more at risk for heart attacks. And they found one patient that had a single mutation in his LDL family, so these are familial genetics, a patient whose family had a single mutation in their LDL receptor, and if they had carried both mutations, so they were homozygote for that mutation, those members of the family died of heart attacks at age 20, in their early 20s. They had extremely high LDL. If they were heterozygotes, so had only one copy, bad copy, and one good LDL receptor, they died of early heart attacks, more like 40s and 50s. So they sequenced the LDL receptor and found that that receptor had a mutation in the cytoplasmic tail. And I want to end with a final clicker question that is based on that mutation. So the LDL receptor is normally endocytosed. You have a mutant receptor that changes tyrosine in the cytoplasmic tail to encode phenylalanine. Assume there's only one tyrosine in the receptor. What happens to that receptor?